to learn the controller design, which is the basic requirement for all the converters, power electronics converter for all the applications, will help us to learn this technology for our research. So with this, I invite Mr. Prakash to introduce Priyabrat.
Okay, sir. Dr. Priyabrata Shaw received the VTech degree in Electrical Engineering and Instrumentation Engineering from the Vizu Patnaik University of Technology, Rourkela, India in 2012, and the MTech in Control and Automation from the National Institute of Technology, Rourkela in 2015, and the PhD degree in Power Electronics and Control from the Department of Electrical Engineering, Indian Institute of Technology, Delhi. He is currently working as a senior power electronics engineer with EATON Research Lab, EATON India Innovation Center, Pune, India. Before joining EATON, he was a manager with Shakti Pump India Limited. His research interests include the design of high-frequency power supplies, analysis, modeling, and control of switch mode power converter, grid tie inverter, motor drives, and control theory applications. Dr. Shaw is the recipient of Distinguished Reviewers Award 2019 from IEEE, Transaction on Industrial Electronics. He received the Young Professional of the Year Award 2023 from the IEEE Pune section for his achievement and contribution in the era of power electronics and control system. He is currently serving as an associate editor for the Industrial Power Converter Committee of IEEE Transaction on Industry Application. By this, I would like to request Professor Dev Priyabrat Shaw, sir, to start your talk, sir. Thank you.
Yeah, thank you. Thank you for your welcome notes, and I welcome all the attendees also to my talk. So, is my voice audible? If anyone can confirm. Hi, can anyone confirm if my voice is audible?
Yes, yes.
Thank you. So, to start with, I will, as Dr. Manoranjan mentioned, that I will talk about the DC-DC converter and its controller design analysis part. So, this is my just bio, which already Prakash has introduced me. So, I will not go through this. Just and these are some of my key journals papers, and these are some of my conference papers which I worked on power electronics and its control applications. And this is just a note from the my industry that these are whatever I am sharing is for the sharing knowledge and to share the knowledge across the community for educational purpose. So, and I will start my talk with introducing about my company first. So, Eaton as an organization, it's a global company, and our main motto is to make what matters work. So, in today's world, as you know, like computer, power electronics is one of the emerging field in any of our applications, from household to industrial to any agricultural sector. Also, power electronics is the heart of the design. So, Eaton is also not away from this. So it is also innovating and designing efficient for sustainable power management solution. And Eaton has mainly two sectors. One is electrical and another is industrial sector. So in electrical, we have power distribution and circuit protection unit, in which we have breakers, fuse, and other products which we are selling. And also we have power quality backup and energy storage system, where battery storage along with UPS. All we know, Eaton is well known in UPS system. Similarly, life safety and security, we have many products like harsh and hazardous environments like oil and gas industry applications. We have products like LED and many other solutions. So similarly, control and automation division, nowadays microgrid is one of the emerging area where the controller needs to be there to cooperate among the battery storage system, grid, as well as the renewable sources. Similarly, industrial sectors mainly aerospace, filtration, and vehicle and e-mobility. Like I mentioned, nowadays in aerospace also we are going into more electric aircraft systems. So similarly, as we all know, electric vehicle and e-mobility are the emerging field where traction inverter, DC-DC converters, as well as on OBC onboard chargers are the key fields where power electronics is one of the major area. But also apart from power electronics, EATON works in filtration like contamination monitoring, a solution for liquid system. So all those things are there in EATON. So we have broad portfolio of products. And before going to my talk, as all of you know, this is a conventional boost converter. So as a control expert and control engineer, uh, we should not only see that a boost converter is the purpose of boost converter is to step up the voltage, which the gain is 1 by 1 minus t. However, we also look at the that what is the system. So uh, we should know that if a converter contains how much energy storage elements, that defines its system order. So suppose here there is one inductor and one capacitor, it defines that it is a second order system. Definitely all of uh, us know what is the order of a system from our basic control system theory, and it has one switch and one diode. So that is why it is known as one of the basic converter. And there are also other basic converters like buck boost, Sepik. However, boost converter finds many applications in industry as well as point of load applications, any of the portable devices, solar photovoltaic applications, MPPT systems. So there are many applications like even UPS system where power factor corrections is required, and also our LED drivers. So we know how to design and analyze the conventional boost converter. So here I will go further that how we can also analyze the similar way, how we can analyze higher order converters also, where we can get better performance in terms of gain as well as in terms of other perspective. It is not only the gain, voltage gain that defines a converter, but also others. So to improve the performance of conventional boost converter, there are many literature that proposes higher order converters, because if you see boost converter, the voltage gain is limited. Also, apart from voltage gain, we know that the switch stress, this S switch, the switch stress is same at the output voltage. When we select a converter, we have output voltage rating in our hand, because input voltage keeps on fluctuating. So if output voltage in your hand, then we will design the switch. So here when the diode is conducting, the switch is not conducting, then you will see the voltage across switch will be same as the output voltage. That's why we see high switch and diode voltage stress. Similarly, the capacitor current ripple is very high, because what happens when this diode is off, then this capacitor is charged from the load, and when the diode is conducting, it is charging from the input inductor and input source. So, in order to alleviate some of the shortcomings of conventional boost converter, from the order point of view, I defined the converter. So, there are some third order topologies are proposed in literature, where you can see third order. I mean to say, there is one inductor, two capacitors. So the gain is around 2 minus d by 1 minus d, which is 2 minus d times the gain of the conventional boost converter. Similarly, there are many fourth order topology also defined, but you can see their gain is same as conventional boost. So definitely there is a question why then we have to use this complex system. However, it is not only gain as I told, it is always other performance. Like here you see there is a load side inductor, so definitely the load current ripple and load voltage ripple will be less, and the capacitor selection will be very easy because the ripple part of the load current actually passes through the output capacitor. Similarly, here you see there is a input inductor. So it is always not only the gain, but also the other performance defines the converter. That's why these are some of the topology that reported in IEEE transaction. So in order to go, so in this study, I propose one higher order converter that is derived from the conventional SEPIC converter. So all we know this is conventional SEPIC, which is known as single-ended primary inductor converter, where this is the input side inductor, and we have two inductors and two capacitors. And the gain is same as a buck boost converter. It can step down as well as step up the supply voltage. So to improve its voltage gain to such that it will work as a boost converter, I will show one example how we can modify the topology, because nowadays people are working lot of in converter areas modifying the topology. So it is not a trial and error method. It is always a approach. Suppose here you see during switch conduction, this diode will be turned off. So the stored energy will be the energy from the source will be stored in the inductor and capacitor. And when switch will be turned off, this diode will be conducting and the stored energy will be delivering to the load. So if we can connect some of the intermediate storage elements which can deliver more power to the load, that will definitely improve the voltage at the load side. So here in a modification, I have introduced a charge pump cell or capacitor diode cell, anything we can say. So based on this topology now becomes the gain becomes 1 plus d by 1 minus d. And we can see now the voltage gain is higher than the SEPIC as well as the conventional boost. And it is not only the gain, as I told, there are other performance like you can see SEPIC had lower input current ripple. Now it has also low input current ripple and lower capacitor voltage stress. Like one of the plus point I will mention you people that why voltage stress is critical in any of the device, because when you are selecting a device like capacitor or switches, the voltage stress is a critical parameter, because when voltage stress is high your component selection will be different, and when voltage stress is high your component cost will be high. It will be in switch, it will be same as in your capacitor. When you are purchasing a 50-volt capacitor and when you are purchasing a suppose 200-volt capacitor, definitely the size and the cost will be higher in case of the higher voltage stress switch. So the stress of the capacitor is one of the critical parameter which is reduced here. We will explain how much it is reduced. And similarly, the low switch and diode voltage stress. As in the first slide, I have mentioned that the switch stress is same as the output voltage. Suppose we are trying to operate this converter and the um, previous converter is the same operating point, then we are going to forego the switch stress. So here now the switch stress is reduced as well as diode stress also reduced. So in order to analyze the claims, so we have seen that when the switch is turned on, that is called mode 1, the diode D1 D2 will be turned off, and the as I told the stored energy will be stored in the inductors and capacitors. And when the switch will be off, then the stored energy in the inductor and capacitor will be delivered to the load. That's why this converter works in continuous conduction mode. And to analyze during mode 1, we can list down the voltage across inductors and during mode 2 the voltage across inductor, both the inductors. By as we know, the voltage across a inductors over a cycle will be equal to 0 to operate the inductor in the linear region. Then we can actually average it out, and we can get the voltage relation between the capacitor input output voltages, and eventually we will get the voltage gain expression for the proposed converter. Similarly, if we will derive the capacitor voltage, you can see now the capacitor voltage is a function of input voltage in terms of buck boost gain. Suppose you are operating your capacitor below the zero point 0.5 duty ratio, that the voltage stress across the capacitor will be less than the supply voltage, like buck boost topology. Similarly, switch stress is also less in case of the proposed topology. Here it is not equal to the output voltage, because output voltage expression is 1 plus d by 1 minus d, but the voltage stress expression is 1 by 1 minus d times the gain in supply voltage. So by analyze this steady state performance, we can definitely always in power electronics it is better to plot the characteristics. So here the characteristic is VL1, VL2, IL1. You can see when the voltage across inductors is positive, so- sorry, your inductor current increases linearly, and when your voltage across the inductor negative, then it's decreases, so that your currents should not rise and your core should not saturate. So this is the periodic operation what we call, and this dt time defines the on time, and 1 minus dts time defines the off time of the converter. So by using time domain analysis, you can find the ripple in input current, as well as ripple in the inductor currents, and similarly the steady state in inductor current equations can be obtained. Now, to design any inductor, what we need the ripple requirement, frequency of operation, as well as the peak current flowing through it. So when you have the steady state current equation and you have the inductor current expression, ripple expression, then you can always find the peak and minimum current through the inductor. Similarly, through time domain analysis, you can always obtain the capacitor voltage ripple, from which we can design the capacitor required for a specific voltage ripple and for a specific frequency of operation. By using these ripple expression for inductor current and capacitor voltages, the inductors and capacitor design equations are obtained. You can see here, we should design a inductor so that the value should be higher than this value. So it depends on the operating condition, duty ratio, frequency of operation, and the required ripple. Similarly, a capacitor also always depends on operating point, that means load, as well as duty ratio, as well as your frequency operation and ripple. So always here one point I wanted to mention, that when your ripple requirement increases, your desired inductor and capacitor value reduces. So it is inversely proportional. So when there are critical applications where ripple requirements are very less, there you need more inductance value, so that minimum amount of ripple can be ensured. Similarly, the steady state current and voltage values are required to design any capacitor and inductor. Practically, we need to know the voltage across the capacitor and the current flowing through the inductor, and what is the minimum value required, L1 and C1 and other inductance and capacitance values. By using these, we have designed the converter, proposed converter, and these are some of the sample results, practical results I am showing. In one plot here, I am showing the gain variation with respect to duty ratio. The x-axis is duty ratio, and these are open loop results. And this second graph shows the capacitor voltage stress variation. You can see, as I highlighted, the capacitor voltage stress is less. You see, when the duty ratio increases, the capacitor voltage stress increases as the gain increases. But when the suppose at 0.5 duty ratio, when the gain is around 3, you see the capacitor voltage stress is around 1. One means it is normalized with the supply voltage. That means the capacitor stress is equal to the supply voltage even at 0.5 duty ratio. That means it is quite less as compared to boost converter or any of the conventional converter. So the initial motto of developing or modifying the topology is to achieve better performance in terms of gain as well as in terms of capacitor voltage stress, as I mentioned. And now as the converter order is increasing, definitely we will see there is efficiency needs to be improved. Otherwise we can say we have a second and third order converter, why we are going for fourth and fifth order converters. So that's why it for any operating point we need to ensure that the converter at least achieves more than 90 or 95% efficiency, because efficiency is one of the prime requirement in any of the industry or any of the applications. And here we can see when the supply voltage increases, the efficiency goes up and losses comes down. The primary reason for that is in the converters operating around 100 and 200 kilohertz frequency. When the load goes up, then when load increases means your current increases. The current in the circuit increases means your IR drop increases. When your IR drop increases, that means conduction loss becomes high. So conduction loss becomes high means your when supply voltage increasing at a particular load I am talking, then what happens, the for a same load your current becomes low. When current becomes low, the loss decreases and the efficiency goes up for a constant power. So this is the efficiency verification for the proper topology. Now these are the some of the steady state waveforms where the converter is operated at 42 volt in supply voltage and it is boosting around three times, means around 0.5 duty ratio. You can see the input current has lesser ripple, and the primary objective or advantage, you can see the capacitor voltage is also below 42 volt, that is the supply voltage. So even though we have achieved better gain in terms of with respect to conventional topology, however we have achieved better performance in terms of capacitor voltage stress, switch voltage stress, as well as input current ripple. So these are the results to show the steady state behavior of the converter. However, the control from closed loop perspective, we need to ensure the converter should operate at a constant load voltage irrespective of the input voltage or load voltage load current variation. So the to design a controller, what we need and what are the steps, I am going to explain in the next slide. So to see a converter, we always see it's in circuit diagram, but what is its plant model, or what we call in block diagram representation of any DC-DC converters. You can see this is the basic block diagram of the DC-DC converter, where this is my duty ratio is the input to converter, and similarly the supply voltage is also input to converter, and load variation is also input to converter, and the output is your load variation, means your output voltage. So when you change the duty also, your your load voltage varies. When you change the supply voltage also, your load voltage varies. When you change the load also, load change means load current change, your output voltage varies. So this is the dynamic model or block diagram representation of the DC-DC converter, which we will eventually use to design the control. We need to know what we are trying to control and what we are trying to regulate. So the GVD is known as the control to output voltage transfer function, because through by controlling the duty ratio, we are trying to regulate the output voltage. Similarly, the GVG is known as the audio susceptibility or supply voltage to the output voltage transfer function, and similarly the Z naught is known as the output impedance, because it is nothing but the output voltage by output current. So it's nothing but representation of the impedance. So these are the model which we are going to use to to design a controller for the DC-DC converters. And to design a controller, the basic steps we need to follow for any of the industry application. We need not to go to any non-linear controller, any sophisticated adaptive controller, because the implementation plays a critical role in the industry, because the implementation effort, cost and time are the critical parameters. So we can follow the basic state space averaging, which we learn from the control system, that x dot equal to x plus bu, and we divide our converter into two operating points like I mentioned. And here, once you have the state space variable, you can definitely average it out, and after averaging you can give a small signal perturbation to get a linearized model. Because our converter is operating at a particular operating point, we are assuming that even though there will be perturbation, the converter will be still around the vicinity or around the operating point. It should not be beyond the operating point. Suppose you are operating the converter at input voltage 42 and the output voltage is around 120 volt. Your input voltage will be 36, 40 and 48. It should vary in this range. 20 to 30% variation is the maximum, but you cannot vary it that 5 volt input voltage becomes 42 to 5 volt. So it goes beyond the linear region, so your converter becomes unstable, because the plant which we considered is a linearized model, so that we can represent it in a block diagram representation. So by perturbing in the duty ratio as well as your state variable. And always remember, for any of the power converter, the state variables are defined as the your system state, which represents the system state, that is inductor current and capacitor voltages, because it indirectly represents the energy in your system. So always, like, energy in inductors are represented by half Li square, and for capacitor it is half Vc square, half Cv square. Then your inductor current and capacitor voltage are the state variable that represents indirectly the energy of your system. Similarly, you can find always the steady state solution for your state space variables by averaging it out, and by perturbing you can always get these equations from which you can obtain the transfer function what we discussed in the previous slide: control to output, input to output, and load to output. So these or transfer function always you can get. And for example, the proposed converter, we have obtained the state variable from the equation by using simple KVL KCL equations, a loop equation, node equation. You can always get A1 B1 C1 D1. So instead of C1 D1, we are writing U1 F1, because C in power electronics represents capacitor, D duty ratio. So to avoid any conflict, so U1 F1, these are not different variables. So for mode 1 you can get this type of equation. Similarly, for mode 2 also you can obtain this type of equation. Now by averaging it out and using the expression I have described in the previous slide, you can always obtain the transfer function like this. So these transfer functions are, this is the transfer function which represents the control to output voltage transfer function. That means for any variation in the duty ratio, what is the variation in the output voltage is shown by this. And for we need to verify for any of the operating point. So this is the operating point we have assumed for the design converter parameters, and we see for this transfer function, this is the system frequency response. So here we see two superimposed plot, and it is why whatever the model we have obtained, is it correct? That is what we are now checking. So this this pink curve shows this analytical model using the state space method, but this blue dotted curve represents the circuit simulation obtained by PSIM. So the circuit is simulated in PSIM, and we obtain this transfer function. So you see, for the low frequency up to 10 to the power 4 hertz, our system means 10 kilohertz. Our system border plot is highly accurate and superimposed. So that's why we can say whatever the model we have obtained is now suitable to design any controller. If these transfer functions are not accurate with the circuit simulation model, then whatever we are going to design any controller will not be accurate enough. That is why in this design, we have also assumed the non-ideal parameters of the inductors, because inductor is not only L1, it has a internal resistance like a series resistance. Similarly, for capacitance also there is ESR, equivalent series resistance. So those are the non-ideal parameters we can also include in our state space modeling to obtain a accurate model, which will eventually help us to design a accurate controller analytically instead of using trial and error methods. So this is now the block diagram representation. I have already explained this converter part, which is nothing but your GVD, GVG and all this transfer function. Now we are going to design a single loop controller which is efficient and simple, so that we can sense the output voltage, and we have a comparator, and we will generate the error. The error will be input to your controller, and the controller will definitely generate a signal which is given to PWM block, and that generates your duty ratio. So in this we are going to design the GC controller, and this LG in simple our control system we know as loop gain. Loop gain is defined in the controller gain into the plant gain, which coming across this loop. So these are the block diagram representation of the closed loop converter system, and we are going to design a single loop voltage mode controller. And here the transfer function equations are also listed so that we can design any controller using this. Now, to design a controller, we assume the what kind of controller we need to use. Like I mentioned, industry requires simple controller structure like PI, PID. So in this, we have designed a PID kind of controller, and for which we use the dominant pole placement methodology to design a controller. So in order to design any controller, you need to have any prerequisite. That means you need to have any desired performance before designing a controller, because what you need to achieve, there will be some closed loop performance like settling time, percentage overshoot, and your gain margin, phase margin. So gain margin, phase margin are the parameters which a designer knows, but for a testing engineer or for a validation engineer, performance validating, who he doesn't know gain margin, phase margin. He knows from the waveform what is the settling time, what is the percentage overshoot, that should be within the range. That's why here we started the design with PO and ST. PO is the percentage overshoot, ST is the settling time. And these expressions are standard expressions you can get from any of the control system books, from which we can always obtain the zeta and omega n equation by solving these two equations. So when we have a PO and ST requirement, we can get zeta and omega n from that. Now from the zeta and omega n, our task is to find the pole location. That means this is the standard complex conjugate pole location for any of the closed loop system. And here I will explain what do we mean by dominant pole. You can ask me always. So dominant pole is the always the rightmost pole of the left half of the S plane. It defines your system characteristics, because when the poles moving away from the imaginary axis, your system becomes very fast. And when the pole comes near to imaginary axis, your system becomes slow. That is why when the system any of the system, when the complex conjugate poles are near to imaginary axis, then that actually dominates your characteristics of the system. That's why these are known as dominant poles. So that is why even though the system has 5 or 6 poles, if we consider 2 poles, rightmost post pole, so that our controller will be designed to achieve the desired performance. So here we need to ensure the non-dominant poles should be away from the dominant pole, so that there will be no cross correlation between them. And if they are close to your dominant poles, then whatever the performance you are trying to define through the dominant poles will not be guaranteed. That you can achieve, but it cannot be guaranteed. So here we have chosen a controller, the and its order is second order, like PID controller, and we call it PID. You can call it PID, PIL, but here it is called PIL because when we see proportional integral lead, that means we have a complex conjugate poles. We are adding complex conjugate zeros through this controller, and we have a real pole at origin, because we know that real pole at origin ensures zero steady state error, because it is the integral part which ensures zero steady state error. Similarly, the pole at high frequency will determines the dynamics performance as well as your system immunity to your noise, because it will add the high frequency roll up. Because in any of the frequency response at high frequency, your transfer function should roll off by minus 20 dB per decade or minus 40 dB per decade, so that at high frequency noise will be attenuated. Should not be amplified. So that is why you need any of the controller, you need a high frequency pole. And these zeros are mainly to actually tune the controller so that the closed loop system performance like percentage overshoot and settling time can be achieved. And these are the mathematical computations by actually substituting the controller into our characteristic equation. Like characteristic equation, you know, always 1 plus plant transfer function into controller transfer function equal to 0. That is the denominator part of your closed loop transfer function is known as the characteristic equation. So once the characteristic equation you find you have, then you can replace the GC by the controller transfer function, and you go on actually simplifying it. Now, when a pole, I am told that your S in the transfer function is always represents a pole. So pole can be actually replaced by a real plus imaginary part quantity. When you are replacing, then you can actually reorganize and separating real and imaginary part, you will get two equations. Now we know the phase margin is defined by the frequency response loop gain transfer function, and phi m is your phase margin. So this is this relation, you know, from this you will get another two equations. Now by solving these two equations, definitely we will get two complex, very actually complex non-linear equation f1 and f2 from this. And we see these f1 and f2 represents only one variable of the controller, that is k3. That means when these complex nonlinear equations are same, that value represents k3. So instead of solving these, I use a graphical method to obtain k3. That means, suppose later I will explain how to obtain this. Then once you obtain k3, you can obtain k1 k2 of the controller. And similarly, there are these are the constant which you need to enforce on the k1 k2 parameters, because your controller coefficient should not be negative. So equating this it to the 0, and it should be greater than 0, then you can obtain constant for k1 and k3, sorry, k3. Now as I told you, these are the two complex equations which depends on frequency. So by actually increasing a array of frequency, you can plot both these functions, and when it is intersecting, that will give you k3. That is simple. So here we have assumed for our converter, if the settling time is around 14 millisecond, and percentage overshoot should be less than 10%, which is a good requirement, and fan margin should be around 75 degree. So these are the parameters or assumption we have made before designing a controller. And these are not the strict assumption. If you are not obtaining a controller, so you can say, sir, settling time is always less is better, so take 9 millisecond. But when you will go through the system dynamics, you will see the open loop transfer function itself has own time constant. You cannot achieve better transient behavior than any of the open loop transfer functions by using a another controller transfer function. So always you have to forego some of the performance because the system itself has its own dynamics. So that's what you need to change on the settling time and percentage overshoot parameters to obtain a desired parameters. Now from this settling time and percentage overshoot equation, you can always obtain the dominant pole like I mentioned in the previous slides, minus zeta omega n plus or minus j omega d. Omega d is your omega n in root over of 1 minus zeta square. So those are the equation through which you can obtain. And now obtaining this k3, and by using the equation I have described before, you can obtain k2 and k3. Now this final controller is obtained here. You see now whether we have achieved whatever we have required or not. Now go to the pole zero map. This is the closed loop pole zero map. I have zoomed here. You see this exactly represents minus 286 plus or minus 390, which was desired. So the dominant pole is placed at the desired location. Now we need to verify whether our settling time and overshoot are defined or not. And this is the frequency response border diagram which shows the phase margin exactly 75, which we have actually taken before the controller design. So now we can see this is 75 phase margin. Gain margin is also adequate, which is around 16 dB. So any converter you are designing, you should maintain minimum of 6 to 10 dB, not less than that, so that your system will be robust. So now if you are seeing, you see this is the step response, analytical step response. You will see that this step response, one second. So this step response shows at any of the operating point, in all cases your settling time is less than 14 millisecond, 14 15 millisecond, and less than 10% overshoot. You see overshoot is less than 10%. So these are the step response analytically you can obtain after getting the your designed controller. Now we will verify this in experimental platform. So here at, at the supply voltage of 36, we obtained that settling time is around 14 millisecond. You see when I am actually increasing the voltage, the settling time even goes low. So in all these cases we can see, we can see the settling time is less than 14 millisecond, which we have actually assumed. So how we can able to define the performance and we can able to achieve the performance using the design systematic controller design approach. It is not a trial and if you are doing trial and error, you cannot achieve your desired performance. You can always regulate it at the required output voltage, but when there is supply voltage load voltage variation, your controller may not work. Your controller system, the control system may be unstable. So those are the things going to happen. So here we know what is the range at which we can actually vary our input and get the performance. And these are the plots which shows the load supply voltage variation. So here this around 18 volt supply voltage variation, you see, your supply voltage is varied from 36 to 48, 12 volt. Here the output has some transient, then it is settling out within 13, 14 millisecond of time. Similarly, for the load variation, you see there is very minimal impact and the settling time is even very low. So these are some of the experimental results which showed the effectiveness of the controller which we have designed through the dominant pole placement method. There are numerous methods, numerical methods which we can assume and adapt and analyze to design any controller instead of doing trial and error methods. And these are the summary which I have discussed today, that operational principles, steady state analysis and design methods are presented for conventional and proposed topologies. The voltage mode controller design method is presented using dominant pole placement method, and some experimental results are shown to demonstrate the steady state and dynamic performance. Similarly, the state space analysis and small signal modeling also presented, which will be extended to any of the higher order DC-DC converter as well. And these are some of the key references which definitely you can follow for this presentation. And thank you. Any of questions are always welcome.
Participants can unmute their mic and ask the expert for queries.
Yes, sure.
Good afternoon, sir. I'm Stuti Patra, and I would like to ask a question
Mhm.
regarding the control methodology.
Sure, sure.
Sir, I want to ask what are the other methods except pole placement technique? Can we go for some other method? Uh, some
Yes.
examples.
Yes. So examples will be there are many methods as I told. So you can always follow some of the papers. Also, they present the design based on gain margin and phase margin. So your initial assumption will be some required gain margin and phase margin. You will land up with some controller, PI controller or PID controller based on your requirement. Similarly, there are also some robust control methodology. So this pole placement controller may not be robust enough. That means because what do you mean by robust controller? When there will be variation in the input voltage and load current, then your controller should also guarantee the desired performance, or it should not be violating the performance. So that is why in pole placement technology, as you are very much concerned about the closed loop performance, that means your settling time and percentage overshoot. So you need to get that output in within the range. So similarly, we can go to other performance based on your requirement. Suppose your requirement is stability, you go with gain margin and phase margin. Whatever may be the condition, your system may not be unstable. And if your desired is robustness, you can go to many of the methods like sensitivity method and also Kharitonov theorem. There are all such methods are there. Similarly, as we read from our basic control system theory, there are Ziegler-Nichols method of tuning. So there you only actually ensure a steady state performance as well as some of the transient performance, but may not be all the performance of the closed loop system. So there are many such methods. Definitely you can follow based on your requirements.
Thank you, sir. Sir, actually, I want to ask about right hand poles. Those are normally present in some non-minimum phase systems. So, how do we
Sorry,
uh,
Shruti, if I want to correct, there is no right half plane poles. There is right half
right hand
plane
zero
zeros.
zero zero?
Yes.
Yes, sorry, sir. Right
Uh,
hand zeros. So, how can we means what are the methods to avoid that zeros, and how can we control the converter system to avoid the influence of those RHP zeros?
mhm. So definitely this RHP0 comes when there will be in similar to boost converter topology, you come across the RHP0. So when there will be RHP0, you want to add some poles so that the system will cancel the impact of the zero. Okay, that is the first approach. Second approach is definitely you need to check what is the frequency at which your RHP0 is present. If your RHP0 is present at very high frequency, then you no need to worry. You go for basic PI controller, you design it, it will work. But if your RHP0 is very near to imaginary axis, or it is within the near to the imaginary axis at low frequency, then you need to ensure the impact of RHP0 needs to be cancelled, because your RHP0 location also depends on your operating point as well as the components values as well as the duty ratio. So when designing a converter, when you see there is a RHP0 at low frequency, definitely you can redesign your converter and make the RHP0 should be at very high frequency so that its impact can be neglected. That is first approach. Second approach, you can definitely add any of the poles to actually minimize its effect, because your RHP0, you think of body plot, when there will be RHP0, it will actually add some phase to the system. So your system becomes more sluggish. System becomes slow. So that is why when there is RSP0, you can definitely design a slow controller. There is no problem. When you are going to design a fast controller, you have RSP0, you have the problem. So that is why always it is recommended for any RSP0 controller, you need to system, RSP0 system, you need to verify the frequency of the RHP0. Then you go to the design of controller. And if you are going for any non-linear controller, then the pole zero concept itself vanishes. So there is no RHP0, because you are going for non-linear controller. Then RHP zero poles concept comes when you are thinking of linearizing. If you are not linearizing, you are going for any non-linear controller design, then your RSP0 impact will not affect your system performance. I think is it answers your question.
Yes, sir. Actually, sir, what are some of the nonlinear controller techniques that we can employ for means for minimizing this RHP0
So I will
RHP0?
recommend, yes. I will recommend any sliding mode controllers are very effective for switching systems, because in sliding mode you have your inherent switching. So definitely that will be one of the best non-linear controllers. And other state feedback linearization, but feedback linearization will land up very complex control methodology which may not be implementable. But nowadays there are many high processing speed and high memory processors are available, so people are also going for feedback linearization method, because feedback linearization you have some freedom to implement the controller operating point. But when the system becomes more complex, like system order increases, then you have a difficulty in implementing the state feedback controllers, or kind of your feedback linearization method. So I would suggest some of the techniques uses that your sliding mode control is definitely useful.
Okay, thank you, sir. Thank you for
Sir,
your.
sir, hello, sir.
Yes.
Sorry, sir. Basically, sir, I want to know clarify my one doubt, sir, regarding the some says optimal and robust controllers. I sometimes use interchangeably, but like H infinity and Gaussian controllers, we say optimal or robust. So, sir, in what sense we say means something is robust or optimal? Means because of they have capability to perform well in case of uncertainty. Like, sir, you mentioned sliding mode observer. So means
Mhm.
what when we say, sir, something is robust or optimal, sir?
Yeah. So optimal and robust, both the words are qualitative words. So now, but from robust perspective, so actually these two words, if we will say from control perspective, these are two means kind of opposing performance. Suppose you want a controller to be optimal. Optimal means it should work as per the design best. Suppose you are means I am taking practical example. Suppose you need settling time of 10 millisecond and overshoot is around 10%. So optimal control should not deviate. That's why it is called optimal. But your robust controller will ensure your performance stability, but it cannot guarantee your performance. It will ensure, okay, it should be less or around, but it may not be exactly same as whatever you have desired. That's why robust controller always you have to forego some of the performance, very strict performance. So that's why I will say another words, robust controllers are slightly slower controllers, because when you want to operate your system at different operating point and you want your system to be stable, that is what robust means. Suppose you have designed a controller for 36 volt 100 volt output, it should work at 30 volt also, it should work at 20 volt also, you want to ensure. So that means you cannot make a controller fast, because if you are making fast controllers, that means think about, your poles will be far away from the imaginary axis. That means you, once you are trying to again redesign your controller or you need to verify the operating point, then the sensitivity of the pole and zero are very high, so your system becomes unstable. That's why fast controllers are slightly optimal but not robust. So that is why now people are calling optimal robust controller. That means it will kind of trade off. So you want to design a controller which will eventually actually ensure my performance, as well as it will actually satisfy some of the robust criteria. Anything optimal or robust, these words are relative words. You need to have some boundary, it should be robust within that range. Suppose you telling the sir, this is one of the robust controller, its operating range is plus or minus 30% input voltage and plus or minus 50% load variation. Within that range it is robust. If I will take that controller and connect it to my system and I will give a supply voltage variation 50%, then it will not work. I cannot say that you have designed you have not designed a robust controller. So it is robust but within that range. Similarly, optimal also, it is optimum for these operating points, it is not optimum for all operating points. So that is what means by optimum and robust. But the word can be used across multiple domains and multiple perspectives to confuse us, but this is the practical meaning of optimal and robust.
Thank you, sir. So all non-linear controllers are robust nowadays, sir, like
Yes, yes,
Gaussian control.
yes. Why it is because sorry, when there is no point in linearizing. Non-linear means you are not linearizing. So not linearizing means you don't have any information about the operating point. So that is why if you are not giving any information to the controller about operating point, then it needs to be robust throughout the operating point. Na?
Yes, sir.
Yes, so that's why non-linear controllers are robust, because we are not linearizing it around the operating point. We are keeping it open. It should work for these parameters. So that is why non-linear controls are very dominant, where you have operating point variation or kind of process control industries where operating point keeps on changing. But for converters, operating point are very much specified by the designer, very much specified. When you are purchasing any inverter in your home, it will be written na input range, output range, input ripple, output ripple, power factor, everything is mentioned. So that is why operating point is mentioned, means you can linearize. If you are going for non-linear, that is best. Or but you should consider also the implementation issues. You should consider also the things that need to be considered while implementing, and when the systems become complex. When it is basic buck converter, okay, you go for nonlinear controller. When it is multi-level inverter and having LCL filter, or there is a two-stage architecture PFC converter with LLC converter, there doing nonlinear control becomes tedious. Nowadays I will say you practically, I'm working some of the projects where we are operating the converter at open loop itself. That is why when you are operating, when you don't think the variation is so much, you give a duty ratio which is actually achieving your output voltage, and you are not expecting many variation, a lot of variation in input voltage. So what is the point in designing a controller? Getting na? Because a controller design itself lot of effort, lot of complexity. If you will also go to basic control system, open loop closed loop comparison, open loop system closed loop, you go and refer, there is a point, open loop systems have more stability. Closed loop systems are having relatively less stable than open loop system, because in open loop system there is no feedback variation na? It doesn't depends on feedback. So if it is doesn't depends on feedback, then inherently it has stability. Only you give the duty, it will give the parameters. Getting na?
Yes, sir.
Yes.
Thank thank you so much, sir. Thank you, sir.
Welcome.
If participants don't have any other queries, I request all the participants to please turn on their camera. We can take a snapshot. Please turn on your camera.
Requesting the speaker to turn off the sharing, please.
Oh, sorry.
Okay, thank you. Thank you, Priyabrat, for accepting the invitation and making it out with your busy schedule. Thank you. Thank you all the participants for your patience. So tomorrow the session will start at
Thank you
9
all.
o'clock. Okay. Thank you, Priyabrat. Thank you.
Yeah. Thank you all. Have a good day. Bye.
Yeah, tomorrow session will start at 9 o'clock. Please join. And the feedback for today's session is shared in the chat box. You can please fill it up.
Tomorrow we will be having two sessions. First session at 9 o'clock, and it will continue up to 11 o'clock. And the second session